Hey everyone, we're back with yet another Chegg office hours for Organic Chemistry 1. So once again, I'm coming to you every Tuesday at 5 p.m. Pacific time with Chegg to do some study sessions here for Organic Chemistry 1. So check out the QR code on the top left if you're interested in seeing what other office hours Chegg is offering. They're doing math, all kinds of other stuff. So you can get help on all your courses this semester. Once again, here we're focusing on Organic Chemistry 1. We're in the live chat. I'm taking questions. So feel free to ask questions in the live chat. Please keep them oriented on Organic Chemistry 1 content. Feel free to ask questions about the problems I'm going over, but also feel free to ask any other question pertaining to Organic Chemistry 1 content. I have some stuff that I like to cover because I'm sort of targeting where I think most of you might be in your semester right now. But I'm totally happy to take other questions that are not related to the exact practice problems I'm looking at. So anyway, let's go ahead and get started. So remember last time we started doing some spectroscopy stuff, and that is something that a lot of students have a hard time with. So I definitely want to go over the basics of spectroscopy more than once here. And so definitely NMR is probably the most confusing, I would say, for many students. So here's a question that says, match the protons to their respective peaks on this NMR spectrum. So once again, last week, and for just getting into this topic, it can be very daunting. You're looking at this thing, you've got lines, you don't know what you're looking at. The simplest way to look at this is that there's three pieces of information that we're looking for when it comes to assigning resonances on an NMR spectrum. Number one, you're looking at chemical shift. And chemical shift is where the resonance sits on that horizontal axis. So where is the peak here? More left or more right? That's called chemical shift. That has to do with how close protons are to an electronegative element. If they're very close to something like an oxygen or halogen, there'll be more downfield. That's downfield to the left. If they're not as close to those elements, there'll be more upfield. So back up that way. Right. The second bit of information is the integration. So that's how tall the peak is. More literally, it's the area under the peak, just like integration in calculus. But we can also just think of it as how big the peak is, how tall it is. And then the third would be the splitting pattern. You can see that these peaks are split up into groups of smaller peaks. This one looks like 3 little peaks. This is like 4 or 5. This is another 3. And so those are the 3 criteria that we're looking at. We're looking at chemical shift, we're looking at integration, and we're looking at splitting patterns. So we're going to assign these protons, and I'm actually just going to ask a question here because I'm not seeing anybody in the chat, but maybe just nobody has left a comment yet. But anyway, so we've got 3 sets of chemically equivalent protons. Now, generally, protons that are on the same carbon are chemically equivalent. There are exceptions to that, like, for example, on alkynyl protons. If 2 protons that are on the same carbon participating in a double bond, those may not be chemically equivalent. Depends on what else is there. But generally speaking, these are all going to be the protons on the same carbon will be chemically equivalent, and that's because they see the same chemical environment, right? So as sigma bonds rotate, those groups, like this CH3 group is rotating, so those 3 protons are going to be able to see all the same environment here. From both Chegg and accounts. Just want to make a comment here that I'm not seeing any of the comments in my feed for some reason. Maybe that will start really soon. Anyway, let's go ahead and do this one in the meantime. So what would we expect to see? Let's say that these protons are group 1, these protons on the CH2 are group 2, and these ones are group 3. Let's go like that. So for number 1 there, what would we expect to see? Well, it's 3 protons, so we would expect to see them integrated to 3. It's a peak integrated to 3. And we would expect to see it relatively upfield, right, because it is nowhere near the bromine atom. And then we would expect it to be a triplet because the splitting pattern is based on the n+1 rule. So what you do is you figure out how many protons are on neighboring carbons, and then you add 1. So for these protons here, those C2 next door. So the resonance generated by these 3 protons is split by these 2 protons. 2 plus 1 is 3. So the resonance pertaining to this methyl group, or the 3 protons on the methyl group, should be a triplet. Then for number 2, we're going to get that integrated to 2. And we're going to see that kind of in the middle. Let's just call it in the middle because it's closer to the bromine than the methyl, but not as close as this CH2 right here. And that will be heavily split. We're going to call that a multiplet because it's split quite a lot. Right, we've got 3 protons on this side, 2 protons on that side. 5 plus 1 is 6. It'll be split into 6 little peaks. And once you have that many peaks, we just call it a multiplet. And then number 3 there is again going to be integrated to 2. And we should see that the most downfield because it is the closest to the bromine atom. And that should be a triplet as well, right? Because these 2 protons see these 2 protons next door. That is a triplet. And so now it's time to make our assignments. So do we have a 3H upfield triplet? Yes, we do. Right there. It's the only one integrated to 3. It is a triplet, and it is the most upfield. So that's certainly going to be number 1. Number 2, do we have a 2H multiplet in the middle? And we do. We have 2H. It's in the middle of the other 2 peaks, and it is a multiplet. It's hard to see, right? With a multiplet, it gets hard to be able to count all the smaller peaks, but we'll trust that that's 6 there. Yeah, unfortunately, I still can't see the chat. Just saying if I can't see them, and perhaps they can be pasted into this private chat, but maybe they'll show up soon. And then lastly, number 3, we have a 2H downfield triplet. So here's 2H. It's the most downfield, and it is a triplet. So that looks good. So when you're doing these assignments, you really want to try to corroborate the peak assignment with all 3 of these data, right? You need integration, you need chemical shift, and you need splitting pattern. And if all 3 of those agree on the assignment, then you can be really confident that you got the right assignment. And obviously, this is a very, very simple example, right? We're talking about a 3-carbon molecule, but these are the same principles that dictate assignment on NMR spectra for even much more complicated examples. There start to be other factors like coupling constants when it gets really tricky, but this is really the name of the game: chemical shift, integration, and splitting patterns. It's going to get you pretty far. So as long as you understand these principles, we can use them to look at other stuff, other spectra. So that's NMR. We'll do a little more NMR in a little bit. Let's move on here. So number 2, draw the product of the following transformation. So we have this substituted benzene. We have isopropyl benzene, and these are the conditions for nitration. Okay. So we are going to nitrate this substituted benzene. So that means we're going to put an NO2 group on there. Now, the question is where? If this was simply benzene, we could put a nitro group anywhere. It wouldn't matter. All the carbons are equivalent anyway. But we have this alkyl group, and this alkyl group is it is an ortho-para director, right? Alkyl groups are weakly electron donating, and electron donating groups are ortho-para directors because they that is the pathway that gives the plus charge in the rhenium ion intermediate directly adjacent to the electron donating group. So when it goes by the ortho or para pathways, it's the most energetically favorable because the carbocation can be directly stabilized by that substituent that's already on there. So remember, ortho, this is the ortho position, this is the meta position, this is para. Also, here's ortho, and here's meta over there. So ortho means next to. Actually, this is called ipso. The group that bears the substituent is called ipso. One away is ortho, two away is meta, and on the other side of the ring is para. And so going by either the ortho or para pathways, we're going to get that better, that more stabilized rhenium ion intermediate. So that's why this is going to be an ortho-para director. And so we're going to get the nitro group at either the ortho or the para position. And so let's draw both of those. So there's our isopropyl group, and then we can have the nitro group there. Or here's our isopropyl group, and we can have the nitro group at the meta position. Now, you are going to get a mixture of these. Chances are, well, it's actually a kind of a toss-up. You'd have to do this and see what the distribution would be, because ortho is favored statistically simply because there are two ortho positions and only one para position. So if collisions are occurring randomly when there's two ortho positions, that makes it twice as likely to get ortho substitution. However, that probability is diminished because of there is some steric hindrance going on with this isopropyl group. So the isopropyl group, there's some bulk to it. It's a little bit of a bulky group, not as bulky as tert-butyl, but still. And so actually that might be enough to skew it towards favoring para. That would be what I would predict. But again, you do get a mixture, and you never know until you go in the lab and you do it. So we're going to get our ortho and our para substituted, di-substituted products. And so that's what that's going to be. So the first part was recognizing that these are the conditions for nitration. The second part was recognizing that this is an ortho-para director because it's an alkyl group. And then the third part was drawing the correct product. That would be it. Okay. So moving on here, we've got label the following compounds as aromatic, anti-aromatic, or non-aromatic. So what are the conditions for aromaticity? This is very important. We need to absolutely memorize these criteria. Number one, the molecule has to be cyclic. Linear molecules are not aromatic ever. They have to be cyclic. They have to be fully planar, right? So they can't, you know, like cyclohexene, right? They have to be all they have to basically be sp2 hybridized. Now, we have to understand that we're looking at the composite resonance structure. So there can be an sp3 carbon on there, but because of the delocalization of the pi electron density, when you look at the composite, it's basically flat anyway. The sp3 character is distributed around, so it's not localized on there. Number three, fully conjugated. So there has to be pi electron density that is delocalized around the entire ring. There cannot be any portion of the ring where the delocalized pi electron density does not go. And so by pi electron density, we're talking about pi bonds, obviously, and we're talking about lone pairs. Lone pairs are also considered pi electrons. So it has to be fully conjugated. There cannot be a part of the ring that where all of the electrons are localized. And four, it has to satisfy Huckel's rule, whereby the number of delocalized electrons in the ring has to equal 4n plus 2, where n is any integer. So if n is 0, we get 2. If n is 1, we get 6. If n is 2, we get 10 and 14 and so forth, going up by multiples of 4 indefinitely. And so any of these numbers is an allowed number of pi electrons that will yield aromaticity if all of the other criteria are satisfied. So with that understood, let's take a look at this first one here. So this is cyclic, obviously. Is it fully planar? Yes, it is, because even though, these all in this individual resonance structure, which once again, remember that individual resonance structures do not exist. Only the composite resonance structure exists. We write discrete resonance structures for ease of describing the molecule, writing mechanisms, and so forth, but they're actually not real. So these, in this resonance structure, we have almost all sp2 carbons and then one sp3 carbon, because we've got a carbanion, right? If it was a carbocation, it would also be sp2. But this is delocalized, right? Because we can do this. We can put this there, and then that can put the anion there, or we can, or we can push this here and put the anion there, or we can push this here and put the anion there, right? We're going to be able to delocalize that all the way around. And so in the other resonance structures, this carbon will be sp2. So in the composite, we're looking at essentially almost entirely sp2 character for every carbon. So it is fully planar. It is fully conjugated, right? There is no part of the molecule where the pi electron density doesn't go. It goes all the way around by resonance. But does it obey Huckel's rule, right? So how many pi electrons do we have? We have 2, 4, 6, 8, right? We have 8 pi electrons. Let's put it up here. 8 pi electrons. So that doesn't satisfy Huckel's rule. Instead, if it obeys 4n, then that makes the molecule anti-aromatic. And so anti-aromatic is a situation where all of the criteria are met, except that it does not obey Huckel's rule. It has 4n pi electrons instead of 4n plus 2. And so if n is 2, we get 8. So 4, 8, 12, 16, right, like that. So 8 is an example of a number of pi electrons that yields anti-aromaticity. And so this one is indeed anti-aromatic. So this is a specifically destabilizing situation, whereas aromaticity is stabilizing, brings the system to a lower energy. Anti-aromaticity brings the system to a higher energy. It is destabilizing. So that anion there makes it anti-aromatic. If there was no formal charge there at all, if this was just a neutral carbon, then it would be non-aromatic because it would not be fully conjugated. Right? This carbon would not be participating in resonance. There'd be no pi electron density getting to that carbon, so it would be non-aromatic. And then finally, if it was a cation, if it was a plus charge, then all of a sudden it would be aromatic, because then everything would apply. It would be fully conjugated again, because the pi bonds would be going over there to neutralize the cation. But then having a plus charge instead of a minus charge, that brings the pi electron count down by 2. So we would have 6 pi electrons. So that would be aromatic if it was a plus charge right there. So 7-membered rings can be aromatic just in certain circumstances, just there. And so yes, anti-aromatic. So now let's move on to this one. So this is cyclic. This is planar. And once again, even though in this resonance structure we do see 4 sp2 carbons and then 1 sp3 oxygen, remember, that resonance structure does not exist. We have to look at the composite where, let me just draw in some lone pairs. This oxygen has 2 lone pairs, right? When oxygen has 2 bonds, it has 2 lone pairs, and one of these can be delocalized, right? So we could put that up there. Now, the other resonance structures are not quite as strongly contributing because they have formal charges, right? If this lone pair goes there, then this oxygen will have a cation, and then one of these carbons will have to have an anion. And so we know that resonance structures where all the atoms are neutral tend to be more strongly contributing than ones with formal charges. Nevertheless, we do have other resonance structures. So you have to look at a composite, and the composite involves pi electron density being delocalized all the way around. It is fully planar, and it is fully conjugated. Right, there's no part of the ring where pi electrons don't go. So now we look to Huckel's rule. How many pi electrons do we have? 2 in this pi bond, 2 in this pi bond. And then here's the trick. So a lot of students get tripped up here. It is actually the case that only one lone pair is going to be delocalized, right? One lone pair needs to be used to achieve complete conjugation of the ring. The other one does not participate. So this, I admit, can be confusing, right? Students will say, well, that oxygen has 2 lone pairs, right? So that's 4 pi electrons plus the other 2 bonds. It's another 4. That's 8. But it's only this Huckel's rule involves only the pi electrons that are delocalized to achieve a complete conjugation, right? So we don't have to count those. And so this is actually going to be 6 pi electrons, and therefore it is aromatic. And so these ones, the heterocycles, you end up just kind of memorizing. 5-membered ring with an atom, two pi bonds, and something in there with lone pairs. It could be sulfur, right? So if it was sulfur, it would be aromatic too. These ones you just kind of see over and over again. That one is aromatic. Okay, moving on to the last one here. This is a 3-membered ring, so it is cyclic. It is planar. This one is fully planar, even just looking at a singular resonance structure, because they're all sp2, right? sp2, 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 because of the cation there. We have only one implied hydrogen, not two. So this is fully planar, even just looking at one resonance structure. It is fully conjugated, right? Because you could put the pi bond there, and then you'd have the plus charge there. And then you could also put the pi bond here and get the plus charge there. And in each case, you'd be neutralizing that one. So you can have a pi bond in each of the 3 positions, and you can have the carbocation on each of the 3 positions. So it is fully conjugated. Now, does it satisfy Huckel's rule? How many pi electrons do we have? In this case, we have only 2. Just the 2 in that pi bond. Remember, this carbocation indicates a lack of, it's electron deficient, right? So that's not pi electrons, that's electron deficiency. So we have only 2 pi electrons, and therefore that does satisfy Huckel's rule. It's the smallest number that satisfies Huckel's rule. So this is actually the simplest aromatic system possible. Is this cyclopropenyl cation is what you would call it. It's a cyclopropene, but it's got a cation there that makes it fully conjugated and therefore aromatic. So that brings this system to a lower energy. That's the aromaticity part. So that's that one. Okay, let's see if I missed anything. Kelsey asks, when do we use heating under reflux? So that's just that's a laboratory technique when you're just doing a reaction and you are getting vapor, and then you want the vapor to recondense and fall back into the reaction flask. That's when you use a reflux condenser. So you've got something on a hot plate, it's boiling, you're getting vapor, and then it hits those cold the cold area that's got cold water running through it, cools that vapor back down, brings it back into the reaction vessel. So that's what heating under reflux means. Lily asks, can you do an explanation of spherical harmonics and what quantum numbers are allowed with a radial solution? So that's either, if you want to talk about quantum numbers in a simple manner, that's going to be Gen Chem. And then if you want to get really in depth, that's going to be in your quantum chemistry course, which is hard. And I don't remember that stuff off the top of my head. But in terms of quantum numbers, remember, we've got N, L, M sub L, and M sub S. So N is the shell, right? So you've got the N equals 1 shell, N equals 2 shell, N equals 3 shell, etc. L is the type of orbital. So when L is 0, you've got spherical orbitals. When you've got L equals 1, you've got the p orbitals, which are lobes extending on the 3 axes. When L equals 2, you've got the d orbitals, which are a little stranger looking. And then L equals 3 is f orbitals, which are even stranger looking. I can't mimic them with my hands. M sub L refers to an individual orbital among the set of degenerate orbitals. M sub S is the spin number. So you can fit 2 electrons in each orbital, 1 spin up, 1 spin down. That way does not violate the Pauli exclusion principle. So every electron in an atom has a unique set of quantum numbers. So orbitals are crazy. They're just basically 3-dimensional standing waves. It essentially proves wave-particle duality for electrons, right? These are 3-dimensional waves of probability density that represent regions in space where electrons can be, which is how we got to that from the Bohr model, where we thought we kind of viewed electrons as corpuscles that are orbiting the nucleus, like planets around a star. It's actually not like that, right? An electron is so small that its quantum mechanical behavior, it cannot be ignored. Electrons have a wave-like behavior, and so that's where you get all those. So hopefully that helped a little bit. Kelsey asks, can we do reaction mechanism? Oh, sorry, Ryan. Ryan asks, can we do reaction mechanisms? I have one mechanism on here, so I'm going to get to that one, and then let me know if there's a particular mechanism that you're having trouble with. I can try to address that after that, or I can include that in next week's presentation. So let's move on for now to the next one. So more spectroscopy. We are talking about IR spectroscopy as well. So this is something that is not as powerful as NMR, right? You can't use IR to unambiguously assign a complete structure to a compound. Maybe in certain cases, but only very, very simple molecules. It's not like NMR. Instead, IR is used to discern the presence or absence of particular functional groups, right? Particular functional groups, the bonds in those functional groups will interact with IR light in a particular way. They'll stretch, bend, all these different ways of motion that are induced by the photon. And then whether that gets to the detector or not, it tells us whether that particular functional group is present or not. And so with an IR spectrum, so here is the fingerprint region, and it is harder to parse information out of that, although you certainly can, and you do later on in your studies. That's more of like an advanced laboratory techniques undergraduate course. When you first learn IR, it's just about memorizing a small handful of functional groups, where they show up, what the peak looks like, because they often have very distinct shapes. And so here we're looking at a few things. This right here is a saturated CH stretch. And so by saturated CH, we're talking about alkane protons. So these are protons on carbons that are not participating in pi bonds, right? Protons on carbons that are participating in only sigma bonds, right? So sp3 carbons. And so obviously most organic molecules have that. So this is a very, very common peak, because anything that has, right, it would have to be like, benzene wouldn't have it, but anything that has alkane carbons, alkane protons will have that. So that will be there more often than not. Then right here, this is a carbonyl stretch. So when you see this, it is quite distinct because it is long and thin. So it's very thin and very long. It reaches almost all the way down here, meaning no transmittance, right? So it's a lot of absorption there of that frequency. And it's at this very particular wave number, which is around, what would you call that? 1700, something along those lines, 1700 inverse centimeters. And so when you see a carbonyl stretch, it's very simple. You just know that there's a carbonyl. And if you don't see a carbonyl stretch, you know that there's not a carbonyl, right? It's simple one way or the other. So we know that our compound has to have a carbonyl. And so which of these has that? Well, that would just be this one, right? So the presence of the carbonyl tells us that it's cyclohexanone. Now, we should be very clear that it would be very, very difficult to discern between cyclohexanone and, say, cyclopentanone, right? That would be very hard to tell, because all this is telling us is that there's a carbonyl. And so this, and then another molecule with a very similar carbonyl, like another ketone, another cyclic ketone even, it's going to be very hard to tell from an IR spectrum. You'd need NMR for that. But this one is going to have the carbonyl stretch. It's going to have the saturated CH stretch. So it's not that having this stretch means it is a fully saturated hydrocarbon, right? There can be other functionality on it. All this says is that this functionality is also present. So every functional group is going to show up. If there are other functional groups, that will also show up. And then the other one that we sometimes see is the OH stretch, and that usually shows up here. It's very broad and smooth, this kind of rounded peak. And so that's generally in this region. It's always to the left of the saturated CH stretch. And if we had that, we would know it would be an alcohol, but we do not see that. So we know that there's not a hydroxyl. We see the carbonyl stretch. So that's the one we're going to go with. So that's kind of the extent, more or less, at least in most courses for Organic Chemistry 1. For most professors, probably going to be enough to just be able to identify 5 or so of these functional groups. Lesson notes, Danny, is the part below 1500 centimeters in wave number in IR spectrum useless? So no, it definitely is not useless. And, laboratory chemists, if they were actually working in the lab, if they were using IR for one reason or another, it's a little bit outdated, but you can still get something out of it. This is not useless. It's called the fingerprint region. And so things like if you're distinguishing between ortho, meta, and para substitution, that'll show up here. If you have like a disubstituted benzene ring, whether it's ortho, meta, or para disubstituted, you can get that kind of information from this region. So it's not useless. It just goes beyond the scope of a typical organic chemistry 1 course. You're probably going to come back to that in more like a 3rd year spectroscopy course. So we won't talk about that now. All right, match the protons to their respective peaks on the NMR spectrum. So let's do one more NMR. Actually, I think I have another one too after this. But so once again, we're talking about chemical shift, we're talking about integration, and we're talking about splitting patterns. That's all we need to worry about right now. So the best thing to do is to predict what kind of peaks you would find based on the protons that are in the molecule. So we have, remember, the protons on the same carbon are almost always chemically equivalent. And so let's say that right here, okay, let's call this 1, we'll call this 2, and then we'll call these ones 3. And so 1 is going to be a 3H. It's going to be integrated to 3. It is going to be, we'll call it a pretty upfield, right? Because it is the furthest away. So the electronegative atom here is the oxygen. The closer the protons are to the oxygen, that oxygen is pulling electron density away from neighboring atoms. So if it is pulling electron density, then it is pulling the electron density around each proton away from the nucleus of that proton, which is called deshielding. It's a deshielding effect when protons are near electronegative atoms. So the more deshielded it is, the farther left it shows up on the spectrum. Downfield is to the left, upfield is to the right. So near more electronegative stuff, more downfield. Farther away from electronegative stuff, upfield. So these are the furthest away from the oxygen, so those will be the most upfield. And we will expect that to be split into a triplet because we see 2 protons next door. 2, and then remember it's the n+1 rule. So 2 + 1 is 3. These protons, the resonance corresponding to these protons on the methyl group, will be split into 3 smaller peaks, or a triplet. Now 2 is going to be integrated to 2, so 2H. And it'll be, comparing this and this, it may be difficult to predict which will be more downfield. And you know what? Sometimes you don't need it. So let's just skip it, right? You don't have to have every single datum perfectly predicted. Sometimes it's enough to just go by integration or splitting or whatever it is. So these protons and these protons, they're both on a carbon that is adjacent to the carbonyl. So we might not expect a dramatic difference in chemical shift. And in fact, we might not be able to predict it. So we can ignore that for now. But the splitting, we know. This is going to be a quartet. So let's call it a quartet. And then let's move on to the third one. So this one is going to be integrated to 3. And then again, we said that we're going to maybe not even worry about predicting chemical shift because we aren't immediately sure which one is going to be more downfield. And then we know that this is going to be a singlet. It's going to be a singlet because there are no neighboring protons. The protons on this carbon, if we go next door, that's this carbon, and this carbon does not bear any hydrogen atoms. There are no protons next door, so N is 0. 0 + 1 is 1, so it'll remain 1 peak, a singlet, okay? So now we're ready to do our assignments. Do we have a 3H upfield triplet? Yes, we do. This one is integrated to 3. It is the most upfield, and it is clearly a triplet, so that is peak 1. Then do we have a 2H quartet? And remember, we didn't know where the chemical shift might put it, but it turns out that being a 2H quartet is more than enough information to make the assignment. Here is a 2H quartet right here. As it turned out, it was slightly more downfield, slightly more deshielded than the other peak, but that's okay. We're going to call it 2. And then we have a 3H singlet. Here's the only singlet. It is integrated to 3. It's right here near the other peak. And so that's going to be 3 right there. So there is our completely unambiguous assignment of this NMR spectrum, which we achieved by figuring out which protons are chemically equivalent and grouping them. So we figured out we have 3 sets of chemically equivalent protons, which would cause us to expect 3 peaks, and there are 3 peaks. Then we assigned the expected integration, roughly the position due to chemical shift, if possible. If not, it's not important. And then the splitting pattern. So we made those predictions based on those 3 criteria, and then we saw that the assignment was very easy. So that's another simple NMR one. Okay, let's do one more because we're hot on it. And oh, let me check for questions here. No, yeah, same. And so you'll get asked NMR questions in different ways, right? You may be given a structure and asked to assign the peaks, but you may be given a spectrum and asked to determine the structure, right, from options or not, right? You could be given the spectrum and an either an empirical or a molecular formula, maybe a molecular formula, right? You could be given a molecular formula and a spectrum and asked to draw the structure, or you could not even be given a molecular formula. That would be a little hard. You'd have to probably be given IR data or something else in there as well to get an idea of what the functional groups might be. But here we have some options, and we're gonna go between them. So the first thing we can do is see that we have 2 peaks. So this looks a little funky, but so these are insets, right? This is this peak expanded, and then this is this peak expanded. So we see that we have a triplet, and we're not even sure what the integration is. We're not even given the integration. So we're going to have to rely on chemical shift and splitting to make this assignment. But we have a triplet that's more downfield, and then we have a multiplet that's more upfield. We'll call it a quintet. Looks like a quintet to me. And so first of all, sometimes you can eliminate possibilities just based on the number of peaks without even looking at where they are, how tall they are, or what the splitting patterns are. It's just about the number of chemically equivalent protons. How many resonances should we expect? So here we have these are chemically equivalent, and then that one. So we would expect 2 peaks there. That works. Here, we would expect this, there's 3 protons there, 2 protons there, and 2 protons there. So those are 3 distinct sets of chemically equivalent protons. So we would expect 3 peaks if this was the compound. So this is not good. We don't even have to look at splitting or any of that stuff. We know it's not going to be that one. Over here, these are chemically equivalent, and then that one. So that looks good. We would need 2 peaks on that. So we're undecided right as of now, right? Now we have to go into looking at chemical shift and splitting, and we don't even have to worry about integration because we're not given integration data, right? It looks like this the 3H is integrated higher, but it is genuinely hard to tell, right? Because the more smaller peaks you have, it gets broader, but when it gets broader, it gets shorter, but it is wider. And integration is actually area under the curve. It's not height. It's literally the area under a curve, and therefore under the resonance. So the broader it gets, the more area there is under there, which can be misleading, right? It's not just peak height. You can't just look at that and determine integration that way. You actually assign it on the computer. The computer does it for you. You highlight it, and it gives you the relative integrations based on pixels. And so so let's do the assignment. Let's assign chemical shift and splitting. So here we would expect these guys. This is going to be more downfield. We can say that we would expect it to be integrated to 4. So just to get a relative value there, just to get a sense of it. And then we're going to expect this to be a triplet, right? Because, and so this is a little tricky, right? The protons, the protons here see these two next door. The protons here also see these 2 next door. So we don't count it twice, right? The way that we want to think about this is take any of these 4 protons. If you take one of these protons, it sees 2 protons next door, so it's split into a triplet. Then the other hydrogen there sees the same thing, so it yields the same resonance, but it amplifies it, right? And then these protons over here see that make the exact same resonance, and so it amplifies it further. And then the 4th one. So each proton is yielding a resonance that is being split into a triplet by the 2 protons right there. And it's just that 4 of them amplifies it to a 4H integration, right? So that's how we want to count that, right? Because of the symmetry of the molecule, you can have protons on different carbons that are chemically equivalent. So we want to bear that in mind. If this chlorine weren't there, or it was something else like a fluorine, then it wouldn't be chemically equivalent anymore. We'd have 3 peaks. But this is symmetrical. So we've got a downfield 4H triplet, and then we've got an upfield 2H multiplet, and we'll call it a quintet, right? Because these 2 protons each see 1, 2, 3, 4 next door. So here we do count them all because the proton really does see 4 protons next door. The 2 on that one and the 2 on that one. 4 plus 1 is 5. It's going to be split into 5 smaller peaks. So that's our prediction there. Over here, we've got this will be more upfield. It'll be integrated to 6, right? We've got 2 methyl groups. So 3 over there, 3 over there. And it'll be split into a doublet, right? Because each of these protons sees only 1 implied hydrogen next door. That's it. So now we want to do this one. This is going to be more downfield because it is closer to the chlorine, right? Here's the chlorine. That's the electronegative element that is doing the de-shielding. So if the proton is on the same carbon that's very close to the chlorine, it'll be more de-shielded. It'll be more downfield. But it is integrated to 1, and this will be a very messy multiplet, right? It sees 6 protons next door, so it's going to be split into 7 smaller peaks. Once you get to about that, it gets harder to discern the individual smaller peaks. We just call it a multiplet at that point. So which of these compounds matches the spectrum? So do we see a downfield triplet and an upfield quintet? Yes, we do. This is a downfield triplet, and this is an upfield quintet, or it looks that way. Over here, do we see an upfield doublet and a downfield multiplet? No, we don't, right? The upfield one is not a doublet. It's clearly split more than a doublet. And then the downfield one is not a multiplet. It's pretty clearly a triplet, right? A triplet is easy to discern. So the splitting patterns don't work for this one here, but they work perfectly for this one. And also, even though we're not given integration values, it does look pretty good, right? The triplet is bigger than the multiplet, and that does correspond or the quintet. The 4H versus 2H does seem to fit that as well. So chemical shift looks good. Splitting looks good, and the integration, even though not given values, does seem to look pretty good. So definitely this is going to be the structure there. This 1,3-dichloropropane. So that'll be that one. Nikolai asks, when it comes to nucleophilic electrophilic reactions, how do I know where the nucleophile electrophile will attack? So so nucleophiles do attacking, and okay, let's say, where do I have more room? Yeah, let's just do it up here. So if we're just doing kind of like an SN2 reaction, and let's say we've got hydroxide. So hydroxide is the nucleophile. So nucleophiles have electron excess, and electrophiles have electron deficiency. And the nucleophilicity and electrophilicity will be in specific sites. And so here, the nucleophilicity is clearly due to the negative charge. And so nucleophiles attack electrophiles. Where's the electrophile? That's going to be right here. It's that carbon, right? The carbon is electron deficient because the electrons in the carbon-bromine bond are being polarized towards the bromine, or at least they will be when the nucleophile approaches. They are roughly similar electronegativity, but it is a very polarizable bond due to the orbital mismatch. The bromine is much larger. So hydroxide can attack the electrophilic site, which is the partial positive carbon, kick off the bromine, and you get the alcohol product. So That's the story of chemistry, right? The story of chemistry is electron excess meets electron deficiency, and they interact. Minusness meets plusness, right? To understand why, that's a question for the physicists, right? To understand why fundamentally electromagnetism causes attraction between opposite charges, we're going to let the physicists worry about that. As chemists, that's a fundamental assumption. That's an axiom that we can, that's axiomatic, right? We know that it happens, and all we have to do is then apply that to compounds. So whenever there's a chemical reaction, we're identifying electron excess in the form of a lone pair, a negative charge, a pi bond, and that is going to be interacting with some electron deficiency, which could be a formal positive charge, could be a partial positive charge due to a polar covalent bond, whatever it is. And then you just make them go. So hopefully that helps. Okay, let's do a couple Newman projections, right? If we're getting some questions about just basic nucleophile, electrophile stuff, it sounds like maybe some people are not quite as far through the curriculum. So let's revisit some of the older stuff. And we're going to draw some Newman projections here. So we want to draw the Newman projection about that bond. So let's draw the front carbon here. The front carbon, we're going to see the three, we see the front carbon and we see the three substituents. We do not see the bond here, and we do not see the carbon behind it, but we see the three substituents here. So we see a methyl going straight down. So remember, this works a lot better if you can visualize yourself in the paper and look at the molecule from the side. And so if we're in there, right, our eyeball, just imagine your eyeball right in there, and the methyl is going straight down. So we've got a CH3 there. This wedge bond is going out of the screen. And so if you're in the screen, you're seeing that up and to your right. So there's the methyl there. And then we have an implied hydrogen up and to the left. Now looking at the back carbon, so we can't see that back carbon. It's obscured by the front carbon, but we can see the three substituents that are connected to it. And so since it's obscured, these bonds are going to originate at the side or at the edge of the circle to indicate they're connecting to the carbon behind the front carbon. And so we're going to see the methyl going down and to the right. We're going to see fluorine on the dash bond. Remember, the dash bond is going further away from us than the screen if we're looking at it top down. But if you're in the screen, you're seeing that down and to your left. So there's the fluorine there. And then here we see CHBr, right? You can either draw that. I mean, we don't have to do it that way, right? We can say, we can do this too. We could draw it like that. However you want to do it, as long as the connectivity is very clear, that is going straight up in the back. So there's our Newman projection. It is a staggered conformation. It's a staggered conformation because all the dihedral angles are 60 degrees. We've got a Gauss interaction right there. We've got a Gauss interaction right there, right? These alkyl groups are adjacent. So there's your Newman projection. All right, let's do one more. So now our eyeball is right there. We're looking right down this bond right here. So here's the front carbon. Here's the back carbon. So the front carbon is the circle. The back carbon's behind the circle. What are all the substituents we see? So here we see the methyl going straight down. So there's that methyl going straight down. We see the bromine. Now if we're on the right side of it. So it's very important. Don't memorize wedge is left and dash is right, or wedge is right and dash is left, because it changes depending on your perspective. It depends on which side of the molecule you're on. So really definitely try your best to imagine yourself in the screen. If I'm in the screen right now, that bromine on the dash bond is going up and to my right because it's further away from the screen from this perspective, further away from us than the screen from this perspective. So bromine is going up and to the right. Then we've got an implied hydrogen going up and to the left. Then on the back carbon, what do we have? We've got methyl going down and to the left from this perspective, right? If the wedge bond is protruding from the screen, then if we're in the screen, we see it on the left, down and to the left there, H3C. You want the carbon connected, so that's why we flip that sometimes. Then we've got the fluorine going down and to the right. And then we've got an isopropyl group going straight up. Don't have to worry about the stereochemistry there. This sigma bond is always rotating, so it doesn't matter. So that is that one there. We've got one gauche interaction. Again, this is also a staggered conformation. Eclipsed would involve the groups right on top of each other. So that's that one. That's a little bit of Newman projection review. No more questions there. Okay, let's do a Diels-Alder. So if we're going to do a retro Diels-Alder, we know that Diels-Alder makes six-membered rings. And so if we're going to retro Diels-Alder, we got to break the six-membered ring. And so we are going to break these bonds and we're going to pull it apart. We're going to pull them apart. So how are we going to do that? We're going to do it like this. Let's put that. So remember, Diels-Alder takes three pi bonds, and you get one pi bond and two sigma. So we're going to have to shuffle around two sigma and one pi to go back to the original situation. So this sigma goes back here to make a pi bond. This pi bond goes back here to make the first pi bond, and then this sigma bond goes back here to make this to make a pi bond there. So if we pull those apart, what do we get? We end up with this as our diene, and then this as our dienophile. So yeah, let's dienophile. And so a couple things here. If you have just one six-membered ring, you know that you had two, right? We're going to pull that apart and we're going to have two different, we're going to have the diene and the dienophile. The diene was not cyclic, right? If it was already cyclic, we'd have the bicyclic system. Number two, the confusing thing here, though, is that if we take this sigma bond and we put it here in between these two carbons, this is already a double bond. That's going to make it a triple bond. You put a bond on top of a pi bond, you get a second pi bond. So you get this this butene here, right? 1, 2, 3, 4. It's a 4-carbon alkyne. It's a 2-butene. And then the diene there. And we can always check, right? We can always go in the forward direction, right? We can always take these and then imagine the electrons cycling in the forward direction. And we can see that we will get that product, right? This pi bond goes there. That's that one. This pi bond goes here to get this sigma bond, right? Here's the new sigma bond. And one of these pi bonds, only one, goes to make this new sigma bond, which leaves a pi bond, right? That leaves one of those pi bonds there. So here are the two new sigma bonds that form. And let's just erase this. Yeah, we don't need those. Okay, so there's your Diels-Alder. Not too hard once you get the hang of it. Okay, let's do one mechanism. We got asked about mechanisms. So let's do the complete mechanism for the following transformation. What is this? This is anti-Markovnikov hydrohalogenation. Anti-Markovnikov hydrohalogenation. We know it's an addition reaction because we've got an alkene substrate. We know it's hydrohalogenation because we have HBr. This is a hydrogen and a halogen. And we know it's anti-Markovnikov because of the peroxides, right? Hydrogen peroxide is going to promote the anti-Markovnikov regiospecificity here. So how does this work, right? Because students will learn this in the absence of peroxides, and that's a very simple mechanism, right? The pi bond grabs the proton, bromide attacks the more substituted carbocation, done and done. Very simple. This one is a little more tricky because of it's going to proceed via a radical mechanism. So the radical mechanism goes like this. We've got hydrogen peroxide, and light and heat will cause this to undergo homolytic bond cleavage. And homolytic bond cleavage means that one electron, the two electrons in the bond, they cleave so that one goes to each atom that was participating in the bond. So that's the opposite of heterolytic bond cleavage, where both of the electrons in the bond go to one atom and not the other. And so we're going to get 2 times the hydroxyl radical. So we denote a radical with a dot like that. It signifies an unpaired electron. Now, the hydroxyl radical is going to interact with HBr. And again, we're going to get, so this is initiation. This is an initiation reaction. Initiation reactions are always endothermic. It's going to require energy to promote that homolytic bond cleavage. Now here, the hydroxyl radical is going to interact with this HBr bond, and we're going to get this. And so these two arrows, remember, they're single-headed arrows. Single-headed arrows denote the motion of one electron, the behavior of one electron. Double-headed arrows indicate two electrons. So we need the single-headed arrows there. And what these two arrows mean is that this electron from the radical and one of the electrons from this bond meet and form a new covalent bond. And then the other one stays there. So that'll give us water, right? HO radical plus another H, that's going to be H2O, plus we're going to get a bromine radical. Now, here's where the regiospecificity comes in. This bromine radical is going to interact with the substrate, and it is going to do so in such a way so as to yield the more stable radical intermediate. So here is this, and one of those pi bonds, or one of those pi electrons, and then the other pi electron in the pi bond is going to stay with that secondary carbon. So this is the key here. This is where we get the regiospecificity. This is going to go to the less substituted carbon so as to leave the more stable possible radical intermediate. Carbon radicals are a form of electron deficiency, just like carbocations. So they're going to follow the same stability trend. A secondary carbocation is more stable than a primary carbocation because it's more substituted. It's more stabilized by hyperconjugation. So a secondary carbon radical is also more stable than a primary radical for the same reason. So that's why the bromine radical goes to the primary carbon and not the secondary. If the bromine radical went to the secondary carbon, you'd be left with a primary carbon radical. That's not good. That's not the more favorable pathway. The bromine radical is going to go to the primary carbon because that leaves the secondary carbon radical, which is better. It's a more energetically favorable pathway. So it's going to go that way. And so these are called propagation steps. Propagation steps can be endothermic or exothermic. It depends on the bond dissociation energies. You have to tally them up. And so initiation steps are always go from covalent species to radical species. Propagation steps go from one radical and one covalent to another radical and another covalent. It's propagating the existence of radicals. You're getting new radicals. Then we can have a termination step, right? Because this is going to go until you get a neutral compound. Well, this is neutral, but it's going to extinguish the radical somehow. So let's have this interact with HBr again. And we're going to go boom, boom. We're going to get that hydrogen radical. And that is going to give us our product. We don't need to, the hydrogen is implied, the one that we just got, so that's there. And then this is going to propagate another bromine radical. So this is why radical species are so harmful, because they it propagates, right? These break bonds and then propagate more radicals, which go and break other bonds. And so you could have a termination step here. It's much more statistically plausible to get this product here. Right, here's our product. This is our anti-Markovnikov hydrohalogenation product. It's anti-Markovnikov because the bromine went to the less substituted carbon of the two that were participating in the pi bond. Primary versus secondary, bromine went to the primary. And it did so for this reason, right? When we look at the mechanism, now we understand the regiospecificity. It's because it proceeds via the more stable radical intermediate in the exact same way that the Markovnikov hydrohalogenation proceeds via the more stable carbocation intermediate. And so statistically speaking, it's more likely to get this through a propagation step because there's a lot of HBr floating around in solution and a lot less hydrogen radical or something like that. But you could get a termination step. And then a termination step is always two radicals joining to form a covalent species, and it is always exothermic, right? When you form covalent bonds, that releases energy. So you form bonds, they go to a lower energy, you're releasing that energy to the surroundings. So yeah, that's the yeah, and we're out of time there. Let me just see if I got any questions there. Does it matter which side the eye is on? So I guess going back to the Newman projections, I think yes, it does, because the arrow is telling you where you need to be, right? If we're looking down this bond, you're sitting right here. You're looking right there. I think hopefully that's what you meant. So yeah, that's the end of that mechanism. I'll try to put in 1 or 2 mechanisms next time, some different ones. And so yeah, that's it for this week. I don't know what happened with the chat. Hopefully next week the chat will be able to show up for me and I can get all of your questions. But this ended up working just fine anyway, filtering the more important ones. And so yeah, once again, check out that QR code if you want to see the other office hours that Chegg is offering. And I will be here for the next, I think, 5 or 6 weeks or so, doing Organic Chemistry 1 review at 5 p.m. Pacific time every Tuesday. So